Hello everyone. In this video, we are going to discuss about this ISC mathematics project for class 12. The topic is explain the concept of increasing and decreasing functions using the geometrical significance of derivative. So this is the important point here. We have to use the geometrical significance of dy dx. So first let us see what is an increasing function and what is a decreasing function. So suppose I'm taking the function f from, say, instead of d I'm taking r, f from r to r, fx equal to, say, x square. Now this is one of my favorite functions because it serves all the needs actually. So how the graph looks here, say this is the axis I'm taking, and we know that the graph of x square looks something like this, though it is not looking properly as the graph, but the graph actually looks like something like this. Here it is origin. So what happens actually here, that if you take the point 1, the output is 1, this height is 1. If you take the point 2, the output becomes 4. If you take the point 3, the output will become 9. So you see the height of this graph is increasing for increasing values of the input. So what you can say, as x increases here along the x-axis, then the value of fx will also increase along the y-axis. So this kind of functions which never decreases, for which you can say f from d to r is a function for which this is happening. So what you can say, for x1 x2, say any 2 points in the domain such that x1 is larger than x2, x2 is larger than x1, then we'll see if this implies that f of x1 is also larger than x2, then this is called an increasing function. As also for the following function, say f from r to r, fx equal to e to the power x. For this one also you see, in the same way, if you take the axis, then you'll see the graph of e to the power x is something like this. On the x, on the two-dimensional plane, it will always look like this. Okay, so then you see the graph of fx is something like this. This will be the graph of it, e to the power x. So here you can see that this value is also the value of e to the power x is also increasing as the value of x is increasing. So this is another example for increasing function. So this we can take as the definition. That for a function f from d to r, if x1 x2 belongs to d such that x1 is less than x2, and this implies f of x1 is less or equals to f of x2, then we can say that the function f is increasing on the domain D. Okay, so this is the definition for increasing function. Now here you see this inequality here is less or equal to type. So that means what? If you get some graph, or if you get some function which is like this, sorry, if you get a function like this where the graph is it is increasing, then at some height it is being parallel to the x-axis, and then it is again increasing. So this also will be considered as an increasing function, though at this stage it is not increasing at all. It is being at the same height throughout this part of x-axis. Say I'm taking from here to here. So here you can see in this part, the value of fx is not increasing. Still, the function will be considered as an increasing function because this inequality is being satisfied. That f of x1 is less or equals to f of x2 for any 2 points. If you take x1 and x2 here on this x-axis here within this range, say x1 is here and x2 is here. So then also you see x1 is less than x2, but f of x1 is equal to f of x2. So the second criteria, that is the equality criteria, is satisfying. That means for increasing function, either f of x1 will be less than f of x2 strictly, and f of x1 can also be f of equal to f of x2. So if any one of the conditions are satisfying, then this function is called an increasing function. So next we are coming to the definition of strictly increasing function. As you have seen this part here, which says for increasing both the condition, any one of the condition can be true. So for strictly increasing functions, we'll see only one condition is true, can be true, and that is the strictly less than sign. Strictly increasing functions. So clearly, as you have seen in the definition of increasing function, here we will take the definition like this. Say, let f from d to r be a function. Obviously, it is a real valued function. And suppose we are taking x1 and x2 belongs to d such that let x1 and x2 belongs to d such that x1 is less than x2, and this implies that f of x1 is strictly less than f of x2. If this happens, then we can say that the function is strictly increasing function. So we'll write then f is called a strictly increasing function, and this function is strictly increasing on the set d. So always remember the nature is defined on the domain. If you extend the domain, the nature may change, but within the domain, if this is happening, then the function will be called an strictly increasing function. So for example, you can see the previous one, that is fx equal to x square, when it is defined on the positive part of x-axis, it will be strictly increasing actually, because from the graph you can realize that it is satisfying only the strictly inequality condition. Means the strictly less than condition is satisfying here for any 2 points. Say here it is x1 and here it is x2. So in no ways for any 2 points this f of x1 and f of x2 can be the same. If this is f of x1, this is f of x2, then they must be different. F of x2 must be larger than f of x1 if x2 is larger than x1. Okay, so it's an example of strictly increasing function. Another one also, you see f from r to r, fx equal to e to the power x, that is also an example of strictly increasing function, because if you see, the graph is like this. The graph is like this. So clearly, these are examples of strictly increasing functions. And you can clearly say here that for the function x square, if x1 is less than x2, then this will imply x1 square is less than x2 square. That means it is f of x1 is less than f of x2, strictly less than f of x2. And also here you can say that if x1 is x1 x2 belongs to R, and you can directly say already that things we have done here, that the domain is R, so x1 x2 must be from R. So if we take this as x1 less than x2, then we can easily say that e to the power x1 is less than e to the power x2, and this means it is f of x1 is less than f of x2, strictly less than. So this is an example of strictly increasing function. So on the contrary, whether there is some definition of decreasing function, something there is there something called decreasing function? So let us see that. So next is the topic decreasing function, and similarly there will be the topic strictly decreasing function. So suppose I'm taking f from D to R such that for x1 x2 belongs to D, where x1 is less than x2, this is implying that f of x1 is becoming greater or equal to f of x2. So then this function f will be called a decreasing function. Then f is called decreasing function. So if you see carefully what it is saying, for smaller values you will get larger output, and for larger inputs you will get smaller values. So let us see one example. Suppose I'm taking f from R difference 0 to R. Okay, the function I'm defining as fx is equal to 1 by x. See why I've taken R difference 0, because at the point 0 it is not defined. So if you see the graph of this, say this is x-axis. Okay, sorry. So this is x-axis and this is y-axis, and here it is the origin. So I'm taking only one part. Actually, okay, let me take the whole thing. So I'm taking the exam graph, taking the two-dimensional plane as this. Sorry, I have to take it like this. Okay, I have to take it like this. Yes. So suppose this is the graph. This is the x-axis and y-axis. Here it is x dash, it is y dash. So then the graph of 1 by x looks like this. One branch is here and the other branch is here at the negative part. So this is the graph of 1 by x. So for 1 will be here somewhere. For 1, we will be getting the output as 1 because the reciprocal of 1 is 1. But for 2, you will get the output as half. But for half, you will get the output as 2. So this is the way how we draw it. It's called the reciprocal function. Okay, so in this way, you will get the thing. So for -1, you will get -1 here. but for -2 you will get -12, which is here. So in this way you are getting the graph, and you can easily see, as for x1 x2 belongs to r difference 0, if x1 is less than x2, this way if you take, then clearly when you are taking the reciprocal, the inequality will change. So clearly you can say f of x1 is greater than f of x2. That means it is becoming a decreasing function. Now, as for the case of increasing function, in the same way for decreasing function also, it can be that if a graph, a function has the graph of this type, say it is decreasing somewhere, at a certain stage it is becoming parallel to the x-axis, and again it can decrease. So this type of functions are also considered as decreasing function only, because here the inequality is being less or equality type. That means f of x1 can be less than f of x2, or it can be equal to f of x2. So if you see this part here, the value of f of x1 and f of x2 will remain same, but it is not violating this condition. So in case of decreasing function, this type of graphs are allowed, but if you are taking it is as strictly decreasing function, then it will not allow this condition. So what will be the case of strictly increasing function? Let us see. So strictly clearly the definition will be like this: f from d to r is a function, and if x1 x2 belongs to the domain such that x1 is less than x2, then this will imply f of x1 is strictly greater than f of x2. If this happens, then we can say that the function is strictly decreasing. Then f is called strictly decreasing. On D, obviously, because it will depend on the domain D. Now, clearly, what we have taken earlier was an example of strictly decreasing function, because 1 by x, you see, it will never become equal to the previous one, though the graph is not like the proper one. Let me draw it as much I can draw properly. This is quite good. So this is x, this is origin, this is y. So you see here, for no points here, no 2 points, you will get f of x1 is equal to f of x2. It will be always for any 2 points x1 and x2, f of x1 will be larger than f of x2. See, this is f of x1 here, this height, and this height is f of x2. So clearly f of x1 is larger than f of x2. So it will always carry this inequality. So it is an example of strictly increasing function. Sorry, strictly decreasing function. F from d to r. Fx is equal to 1 by x. Sorry, it is f from r to r will be x not equals to 0. Now we can take another example of strictly decreasing function, that is cos x. If you take f from r to r, you don't have to take r to r, actually you have to take here a particular interval, you can take the interval 0 pi to r, fx equal to cos x. So what we will get? Okay, I need some portion. I need some portion in the negative part, so I'm taking it here. So if you check, the graph of this will be no, it will not work. I'll take it from here. Yes, the graph of this will be looking like something like this. Here, this point is 1 because cos 0 is 1, and this point here is -1 because this point here will obtain at pi. So this depth is -1. This is -1, and this point here is pi. Let me write it clearly. This point here is -1, and this point here is 1. So you can clearly see it is decreasing all the time, and you can also say that if we take x1 x2 from 0 pi such that x1 is less than x2, then we can say that cos of x1 is greater than cos x2. From the graph also you can verify it. So the graph of this and the function cos x is becoming strictly decreasing function on the interval 0 pi. So these are the definitions and examples of increasing and decreasing functions. Now we have to come to the definition, or you can say explanation, using the idea of derivative. So first of all, let us see what is the significance of derivative. If you remember that we have already done in class 11 that the significance of derivative is that when you are saying a function f from d to r is differentiable, that means you can draw tangents on this. This means you can draw tangents to the curve y is equal to fx. And if you say differentiable on d, then you can say you can draw tangents to the curve y equal to fx for any x belong to d. So suppose this is the graph of fx. Say this is the graph of fx, and this is one of the point x. So you can say this is the height fx, and here this point will be our x comma fx point. The coordinates of this point will be x comma fx. So what is the important thing is that we can draw a tangent here. We can draw a tangent here like this. It is not possible to draw it here using the pen, but I will try to draw it using this straight lines. We can draw a tangent just like this. In this way, we can draw a tangent on the curve at the point x comma fx. And if we draw a tangent like this, then since it is a straight line, we will be getting a slope of this tangent. And this slope is given by the value of dy dx. So this is the geometrical significance of derivative. That the value of the derivative means it is the slope of the tangent at the point at which you are differentiating the function. So what is the link of this significance of derivative with the increasing and decreasing function? You see, if you take an increasing function, the graph will be like this. Say I'm taking an increasing function. Then the graph, say the graph of the increasing function is always like this. It is increasing. So what you see, if you draw a tangent here on this line, okay, let me take the tangent a little bit lighter. Then you will see the tangent will be looking like this. This is the tangent at some point here. And if you see carefully, see that the slope of the tangent, if you extend the tangent a little bit here and the axis also, then you see the slope of the tangent is an acute angle. So the inclination here, so the inclination is theta. You can easily see it is less than 90 degree. That means what? If this theta is less than 90 degree, it is in the acute part. So then what we can say here, the slope, the value of tan theta, since theta is in the first quadrant, so the value of tan theta will be greater than 0. Or if it is being equal to 0 degree, then it will be greater or equals to 0. Now this is the slope of the tangent, and already we have seen using the geometrical significance of derivative that this implies that it is the value of the derivative, or you can say it is the value of the dy dx. So dy dx is greater or equals to 0. This means the tangent to the curve is having a positive slope. So for the function here, say we are taking the function f from d to r. If the graph of the function is having the equation y is equal to fx, then the the derivative of this will be having a positive value, and this means the function is increasing. That you can verify from the graph also. So let us come to the previous examples. One of the examples we have taken previously was f from r to r, I think. Yes, we have taken f from r to r, fx equal to x square. So if you take the derivative, I think we have taken this one also as r plus, because the positive part we have considered. So if you take r plus, you can see here that the derivative will become 2x, and x from r plus means this will be positive always. So when you are taking the function x square on the positive part of x axis, the function is becoming increasing. How the graph looks? If you see carefully, the graph for this will be looking like this. This was the graph for x square, and you see for a tangent at some point of this graph, it will be always making a acute angle. That means the derivative is positive. The slope of the tangent is in the positive part. So in the same way, if you go for e to the power x, so this is the graph actually for e to the power x. If you see carefully, this is the graph here, and you can say that for this one also, the tangent will be always making a positive angle here. The slope of the tangent will be always positive. That means the derivative of the function will be always positive. And we know this because we have already know that f from r to r, fx equal to e to the power x. If this is the function, then f dash x becomes again e to the power x, and exponential functions are always positive. Not even this equality will come. It is strictly greater than 0. So you can see that the derivative is positive here, and we have already seen that the function e to the power x is a strictly increasing function, and this is verified from here. Okay, so this is the idea of strictly increasing and increasing function using the geometrical significance of derivative. So in the same way, we will be able to define the decreasing functions. So if you see for the function f from r difference 0 to r, fx is equal to 1 by x. What is the derivative? F dash x equal to minus 1 by x square. And you see this minus this x square is always greater than 0, greater or equals to 0. So when you are not including 0 for x, it should be taken as x square greater than 0. So if you take the reciprocal, then this 1 by x square and minus 1 by x square, it will be always less than 0. That means the derivative is less than 0. So what you will get here, that the graph is being strictly decreasing. We have already seen it. So now let us see it in the graph. So the graph of this will look like this. And if you draw a tangent here at any point, you will see the tangent will be looking like this. And you can easily see that the tangent here is making an obtuse angle with the positive direction of x-axis. Say it is theta. So it is an obtuse angle. So you can say that tan theta, that is the slope, is less than 0, because theta here will satisfy this inequality. So tan theta is in the theta is the second quadrant. That means tan theta will be negative there. That means you can say dy dx, or you can say it is f dash x is less than 0. So from here you can see if the derivative is less than 0, then the graph will become strictly decreasing. Now let us see some examples where you can say that the equality, if the equality occurs, then we will get some decreasing function, not strictly decreasing. Okay, so we are considering this one, f from so I think this is clear to all of you, the idea of increasing, decreasing, strictly increasing and strictly decreasing function, the definitions, the examples, and the final thing is the geometrical significance of derivative, and how to use this geometrical significance, how we are applying it to distinguish between increasing, decreasing, strictly increasing, and strictly decreasing. So let us sum up here. Point one. First, let us take a function f from d to r, where fx is some particular expression of x, and let us take this as a real valued function. Then we can say that in terms of the derivative, then we can say f is increasing on d if the derivative f dash x is greater or equals to 0 for all x belongs to d. Number two, we will say f is strictly increasing if the derivative of x is strictly greater than 0 for all x belongs to d. Obviously, this strictly increasing on d. In the same way, f is decreasing, f is decreasing on d if f dash x is greater or is less or equals to 0 for all x belongs to d. And number four, f is strictly decreasing on d if f dash x is strictly less than 0 for all x belongs to d. So in the project, what we will do, first of all, we will explain, first of all, we will give an introduction to this concept of increasing and decreasing function. So you can make a Google search for this. First you take this thing. First you give an introduction of the topic. You can search it on Google. You have to give some information about this this increasing and decreasing function. You can do a Google search because you have to do something in the project by your own. Then you can come to the definitions. All the definition you are giving and example. Remember, corresponding to each definition, you should give example with the graph. So it will be very much clear to the examiner what you have understood about this thing. So definitions and examples. Number three, what you are doing is a brief discussion on geometrical significance of derivative. That it is the slope of the tangent. You need to discuss about this. For this, you can go through any book of class 11 and the previous the elementary part of derivatives, the chapter derivative. You will find there the explanation how this the derivative is becoming the slope of the tangent. So that you need to discuss here. And number four is to explain the examples given previously using the geometrical significance. geometrical significance of dividends. And after this, what you can give is the use and applications of this type of function, this increasing and decreasing functions, where you can find these things, this type of functions in nature, or if any point you see here, some which is something different, that you can discuss here. Use and application is one of the things. If you can have any other idea with increasing and decreasing function, you can, if you can link this idea of increasing and decreasing function somewhere else, then that you can explain here with further discussion. You can give this heading further discussion, and then you can discuss your uh, discuss the thing you want to discuss, which is uh, which is a little bit different from the usual things. If you find some link between increasing and decreasing function and any other topic, then you can discuss it here. So this will be your project on increasing and decreasing function, and the rest of the structure that I have given already, you can follow that. And this is the theory. Using this, you prepare your project. So thank you for watching this video.